Hello Game Makers, this is Game Maker Rob, and today we are going to be covering the start of a node system for our XCOM battle system. Before we get to the code, I just want to explain briefly what we're going to be doing and some of the reasons why. Hopefully that will give you a bit of understanding what we're doing. Okay, so in our battlescape, not every cell actually has data, but we do want a node in every cell, regardless, to allow for things like flying and shooting. Rather than just using object instances for nodes like I usually do, I decided to use data structures this time round. I could have updated the existing code where we have, a list of grids of lists, and I could have just made sure that we had a list in every possible cell, regardless of whether there was terrain, and use them for nodes. I decided to keep the nodes separate, make it its own thing. Hopefully that way it will be less confusing to you, I hope. Let me know how it goes anyway. So I also wanted to introduce using arrays and structs to you guys, and there are benefits to each. Ultimately I went with structs because I didn't see a need to loop through each individual node's data like arrays would allow us to do, and also using a struct means we don't need yet another enumerator. It's extra work for us, and making sure we destroy structs on time shouldn't be a problem, which is one of the main downsides of using a struct from what I can tell. So what kind of things do we need to keep in mind when designing our node system? Well, for pathfinding, walls and floors will block movement as well as decoration, and we have to bear in mind that this is a 3D world where you can walk off a roof and land on top of decoration below you, which leads to some potential cases where an actor might get stuck. And I haven't even considered what happens when an actor falls on another actor. There could be some potential cases where an actor gets stuck because he lands on decoration and he's surrounded by tiles that also have decoration, but because decoration will be destructible, I'm going to allow that to happen, and the player can just deal with that as they see fit. Since walls and floors will also be destructible, we will want to be able to update connections between nodes. Doors also count as walls in our code at the moment, and stairs count as decoration, so we will want ways to deal with that, which means less elegant code. And speaking of less elegant code, I rediscovered a stumbling block I had a year ago, roundabouts, when I was first working on XCOM, and that's the draw order. I spent another solid day this weekend seeing how I could best deal with it, but apparently it's a difficult problem for most people, which is why they use 3D. With that in mind, I'll do my best to mitigate any visual draw order problems, but there may still be some which may or may not get fixed. If or when I do finally find a good way that works well, I will definitely update the video. Okay, let's get into the code. Okay, so in the step event of OBJ Battlescape, we've got 2 new regions. In the create area, we have create Battlescape. We're also going to have create node structs. This is our new one. Just zoom in a bit. Okay, so we need a node for every cell, and when I say every cell, I mean for the entirety of the battlescape, up to as high as the maximum levels, which is 12, regardless of whether we have buildings that reach that high or not. And this is to allow us to use them for things like flying and shooting. I haven't 100% finalized all of the code yet, but I'm just trying to make sure we have our options open, so I can't really see a bad side of doing it like this. So we have, let me just kind of show you this stuff right now. We have a double for loop here, which is going to go through all of our cells per level. But there's also 3 different tasks we need to do for our nodes. And rather than have 3 sets of triple for loops like this, I decided to, inside our for-var YY, for-var XX, I decided to check to see what task should be done, and that should avoid us having to do this like 3 times. So that's why I've set it up like this. As always, we have like 100 curly brackets, but this end region is for this region here. This end bracket is for the tasks. This one is for the levels. This is for the YY. This is for the XX. Okay, so once you have this structure down, let me just start at the top and I'll scroll down slowly. So once you have this structure down, we're going to open the first task. I've just changed the names of these 2 arrays. You'll see what they're for in a minute. It was just to kind of give them a similar name so that you'd kind of recognize what they're for. Anyway, in the first task, create a struct for every cell. We're going to have an array called all nodes, which stores all of the nodes, and it has a dimension for the level, a dimension for the XX, and a dimension for the YY. And inside every cell, inside of every entry for this array, we're going to be creating a struct, which is what this equal sign and these curly brackets will do. We don't have to create a variable name. It's going to be created and stored as a number, like lots of things in GameMaker are. So every struct is going to get 2 arrays. This is all the data we need for now. We'll add more later as we need it. But the first array is going to be nodes underscore adj underscore all. Adj stands for adjacent. Basically, regardless of walls or decoration, any adjacent struct that is next to, including diagonally to the struct, is going to get added to this array. This is just on a level per level basis. It doesn't store any structs that are below it or above it. And then nodes walk gets its information when it's created from nodes adj all, but then any nodes that should be blocked because of walls and eventually decoration will be removed or are removed from nodes walk. And this array is what we're going to be using for pathfinding, moving around. Okay, so that's the first task. Then in the second task, fill nodes underscore adj underscore all array. The first thing we want to do is grab the current node that wants to know its neighbors. Then we're going to use a double for loop, which is going to be checking like a 3x3 grid. And if I just switch my camera, so here is a paint file. A paint file that I made about a week ago just to help me visualize how nodes would be blocked off. So the green square is the node that's checking, and this 3x3 grid is the nodes that we want to add as adjacents. The red lines, if you can see them, are walls. So if there's a wall there, then this orange node cannot connect to the green node and vice versa. If there's no other walls, then all of these yellow nodes we can walk to. If there's a wall here, then all 3 of these nodes are blocked from this green node. I'll go into this in more detail when we get to the walking bit. So let's just go back to the adjacent nodes for now. Okay, so we're checking the 3x3 grid. We want to make sure we are within the bounds of the battlescape, which is what this is going to do. This line checks to make sure the XX value is greater than 0, and the YY value is greater than 0, and the XX value is less than the width, and the YY value is less than the height. And obviously when I say XXYY, I mean the edge underscore XXYY, because we're when we start this double for loop, we're starting at YY minus 1 and XX minus 1. So the very first struct is definitely going to have some nodes out of bounds. So anyway, as long as we are within bounds of the battlescape, we want to grab the value of that adjacent node, which we're grabbing from our array, all nodes. I have here a check to say, I think I made this change yesterday, checking to see if add node is -1, but it's never going to be -1. So we're just going to delete that, because we only ever add structs to this. So sorry, we're just going to delete that bit. So as long as we're within bounds of the battlescape, get the adjacent node and add that adjacent node to our nodes edge all array for our current node that we want to check. So just to recap, this node is the one that's checking, and then it checks like this, and all of these nodes get added to its adjacent array, basically. If there is no node, then a -1 gets added instead, which is here. And what we also want to do here is we want to set the middle node to -1. This is because the middle node, again, let me go back to my diagram. The middle node here is itself. We don't want to have itself as its own neighbor node. That's going to cause us problems with pathfinding, I'm sure. So that's why we're doing that. And then the final thing we want to do in this task is copy all of the nodes from nodes edge all into nodes walk, as long as it's not a -1. So any actual structs will get added to our nodes walk array for this particular node. And we're going to be updating this array in our final task, which we'll do next. So we're going to be updating each struct's node walk array. Node walk array based on walls blocking movement. Obviously other things like decoration should block movement as well, but we're going to tackle that in another video. So the first thing we want to do is grab the node that we want to check, and then check it for walls. So floor grid may be undefined because we may be at a higher level. So if it's not undefined, then we're going to get the data list for that cell. If it is undefined, then we are just going to set data to -1, and that means we can just skip the check because there's not going to be any walls or decoration because there's no data. So if there is data, we're going to create a throwaway array called nodes to delete, and hopefully you can tell by the name, it's going to store an array of nodes that we want to delete from this particular node's walking array. So let me switch back to, well, let me tell you this first. So a west wall will block entries 0, 3 and 6, and a north wall will block entries 0, 1 and 2. What do I mean by those numbers? Let me switch to the paint again. So basically this cell is 0, 1, 2, 3, 4, 5, 6, 7, 8. That's what the numbers mean. And when I just checked this task before I recorded it, I realized what I should have said as well for the all adjacent nodes array that every struct has. We want 9 entries even if the entry is a -1, we want to keep it like that so that we can always check what node is in what particular entry. So if it didn't make sense before, if it didn't make sense why we were adding -1s to it, that's why. Okay, so west wall blocks 0, 3, and 6, which is the first column. So all we do is we add to node to delete whatever node is stored in this position for the array, and for 3 and for 6. And we also do the same for north wall. North wall blocks the first row, so 0, 1, and 2. So again, we add those structs to node to delete. West walls and north walls both block the first entry, 0. It doesn't matter if we're adding it to node to delete twice, because all we're doing is checking to see if that node exists in our walking array. If it does, delete it, and if we check for it again, it's not going to be there, so it's no big deal. It saves us a bit of lines as well, a few lines of code. Okay, so now we have an array of nodes that are blocked by this node's walls. What we're going to do is we're going to go through that array, and we are going to do two things. Let me switch back to the paint again. So what we're going to do is, say for example, this node has a west wall. It's going to remove these 3 nodes from this guy's array, but we're also going to remove this guy from each of these 3 nodes arrays as well. So we're going to do like a 2-in-1, and that's going to get rid of almost every case apart from one, which we will do at the end. You'll see that coming. Okay, so for as many nodes to delete there are, get the node that we want to delete. If it's not a -1, because it could be a -1, if the node is not -1, we're going to use a script called arrayFind, which works like DSListFind, in that you give it an array instead of a list and a value, just like you do a DSListFind, and it's going to return -1 or the entry. We'll code this script in a minute. Let me just get through the rest of this block first. So index is going to be -1, or it's going to be an entry. If it's not -1, then we're going to use an existing function arrayDelete to delete that entry from our array. And then, like I said, for each of those nodes that are blocked by the wall, we're going to remove the current node from their arrays as well, which is what these 2 lines deal with. And then we have our closing 2 curly brackets. So this curly bracket matches line 275, the start of the for loop, and this matching bracket is for this line here. So let's go into arrayFind. This is the script. It's really simple. We're passing an array and a value to find. We have a variable called found, which gets set to -1 at the start. We go through the whole array. If we find the value in the array at a position, then we set found as the position. We break out of the loop to stop checking, and either one or two things is going to happen. Either we broke out and found equals a number greater than -1, or found still equals -1 because we checked the whole loop and never found it, so it's just going to return -1. So those are the two things that can happen. That's what the script does. It makes arrays more useful, or just as useful as lists without the problems. So we have done up to here, and then this curly bracket here. So that curly bracket is referring to if data is not equal to -1. So if data equals -1, then we don't need to do anything because there's no data. So the last thing we're going to do in this task is the very last entry, number 8, the bottom right of the adjacent structs. That's the one that isn't covered by what we've just done. So the first thing we want to do is, this is the best way to do it. So before we do this last code, I'm going to show you what it looks like if we don't do this code. It's easier with a visual demonstration of why we have to do this. So basically, you can see if I move the mouse to the corner, then there's still a cell to the bottom right of the cursor that it thinks is connected to the cursor, but the walls should block it, but they don't. And so what we need to do is check to see if there is a north wall to the cell below the cursor. If there's a north wall there, then this cell should be blocked. I'm just wondering now whether we need to do the same for the west wall, like to the right of it, but if we encounter that problem, we will update the code. So that's what this code's going to do. Let me just select it all and then do Control-Shift-K. So run the game. I'm going to run the game again to show you the difference. So with this code now, we no longer have that corner node as a neighbor, which is what we want. So basically, we check to see we're not already on the edge of the battlescape. So if YY plus 1 is less than the height, and and there's data, there's a floor grid to check, and there's actually a list in that data, that floor grid. So as long as these three conditions are true, so we're not at the edge and there's some data there, we're going to check to see if there is a north wall. If there is, then we get the adjacent node that's stored in the very bottom right cell. As long as it's not -1, then we use our array find script to get the index, and if that's not -1, then we delete that node, that bottom right node, from our nodes walk. And that's the end of this region. So let me minimize that. So there we do. That's the vast majority of the code for today. Okay, so in the next state, BS ready, we have a new region which is for the cursor. The first thing we want to do is to calculate where in the grid the cursor is. It's an isometric grid. Well, it's displayed in isometric, so we have to do these calculations to calculate where in the grid the cursor is. And we just want to clamp the cursor to the size of the battlescape we're doing there, just to prevent us from going below 0 or greater than the width and height. And then so we can have the visual display that you've been seeing, where the cursor will show adjacent nodes being read, we need to know which array we should be using. So all we do is we grab whichever node the cursor is over, and then we just save that array inside neighbors. So the next thing you want to do is in the draw event of OBJ Battlescape, you're inside our main for loop here, levels YY XX, and then here testing nodes walk. So if the levels is 0, grab the node. This can be, you know, whatever node's being drawn. If that node is in our neighbors array, so the neighbors array contains all the nodes that the cursor is over, remember? So if this is true, then we're going to draw our grass tile in red, so it displays like a red diamond basically. And we're also going to draw our cursor at the end as well. So if XX is cursor X and YY is cursor Y and levels is 0, then draw our cursor. Obviously everything we're doing today is only really working on the very bottom level, but as long as we can get this working, then we can build upon that as we go. This is why it's going to be a couple of episodes as opposed to just one for this. Let me just check to see if there's anything in the draw GUI that we have. Well, one last thing we have here, if you want to do it, you don't really need it, is these 3 lines. It just shows us the size of the neighbors array, just to make sure, just so we can tell, okay, yeah, that doesn't, because sometimes when we can't really see how many neighbors are inside buildings, and this will give us a better idea of how many there are. There's other ways to check it as well, but it's just another layer of debugging, really. So now we have all that, let's run the game. So you should be able to run the game as well and see everything that I do. It should be the same for you. So we can move our cursor around. If we go to the very edge of the map, this cell here only has 3 neighbors. Obviously, depending on what you have, what kind of battlescape you have, that can be different. But generally on the edges, you know, they have like 5 neighbors. And so you can see in the middle left, neighbors says 5, which is right. In the edge it says 3 for this one, 3 for this one. What's that? I don't know why all those are. Probably some kind of. I don't think it's a problem anyway. This guy has 1 neighbor. Normally he would have 3, but there's 2 north walls blocking him, so that's good. That's working. This guy only has 2. All these have 2. Well, this guy has 3. Well, it says he has 4 neighbors. So I guess we have a problem with that somewhere. Like I said, any kind of issues we have, we will fix them as we go. But this will be the next episode. This guy should only have 3 neighbors, but he has 4. This guy has 6 neighbors. 1, 2, 3, 4, 5. He should only have 5. I'm guessing there's another case I haven't checked for. I was hoping to avoid having to do lots and lots of different checks. That's why I was kind of happy, you know, that I was able to use the west wall and north wall to block 3 at a time. But I guess my method isn't as good as I thought it was. So we have some room for improvement, but it's a start anyway. You know, you can see what we're going for. So if you have something like I do, then you are in the right place. We need to update it next time, but that's not a problem. We have a solid foundation to work from. Thank you for watching, guys. I will catch you next time. Bye for now.